Hello, in this video we shall be looking at rotational motion. Rotational motion is what we are looking at. So, rotational motion is one type of motion. There are different types of motion. So we are looking at one of it, which is rotational motion. So rotational motion is one type of motion. It is a motion of a body in a cycle about a center or an axis. Motion of an object or a body in a cycle about an axis. We call it rotational motion. And the example, rotation of an electric fan blade. You have the fan, the blade, rotating about a fixed point. Other example, movement of a car wheel. Rotation of the earth about its axis. These are some of the examples of rotational motion. And permit me to say that rotational motion is different from circular motion. In the case of circular motion, is the movement of an object or a body in a circular or curved path. So if you have an object moving in a circular or along a curved path, we can say that the object is undergoing circular motion. But in the case of rotational motion, the object is moving in a cycle about a fixed point or axis. I believe with this you have known the difference between rotational motion and circular motion. They are not the same. Okay, let's make progress. Rotational motion is common with rigid bodies. Not every object that can undergo rotational motion. So objects or bodies that can undergo rotational motion, we call them rigid body. So what is a rigid body? A rigid body or object is one that is not deformable. So an object that cannot be deformed. For instance, this paper now, this material, you can deform it, change it into different shape. But when you take, for instance, a stone that you want to undergo rotation, you can't deform it. It is a solid. So we can consider stone as what? A rigid body or a rigid object. So we say that a rigid body or object is one that is non-deformable. And by that we mean that the relative location of all particles of which the object is composed of remain constant. So as the object undergo rotational motion, the relative position of the particles that form the object all remain constant. So we can say that when a rigid object is rotating about a fixed point, every particle on the object rotates through the same angle in a given time interval and has the same angular speed and angular acceleration. I hope with that you know what is a rigid body or a rigid object now. Okay, let's make progress. There are terms that we commonly use in motion. Terms like displacement, velocity, and acceleration. These are terms that we commonly use under motion. In the case of rotational motion, we are talking about angle. So here, emphasis will be on angle. So you hear of angular displacement, angular velocity, angular acceleration. In my earlier video on circular motion, I have defined all this and the mathematical expression for them. Also, the relationship between linear velocity and angular velocity was equally considered. And also linear acceleration and angular acceleration. So please, I advise you to look at that my video on circular motion for more understanding on angular displacement, angular velocity, angular acceleration, and also relationship between linear velocity and angular velocity, linear acceleration and angular acceleration. So please look at the video, look at that video, so that I will not explain it here again. So thank you very much for that. Okay, let's make progress. Please permit me to explain this angular displacement. Is expressed in 3 units. One of it is degree, and in a cycle we have 360 degree in a cycle. The other unit where we can express angular displacement is revolution. Revolution. And one revolution represents one complete turn of 360. So as objects move in a cycle from the starting point to the end, it makes one revolution, which represents complete turn of a cycle, which is 360 degrees. Then the third unit that we can use for angular displacement is radians. And radians is the SI unit for angular displacement. And also in that my video, I emphasize this, that as an object move in a circular path of radius r, covering a distance s, moving from one point A to another point B. This is the angle. So from here we can say that angular displacement is equal to arc length over the radius. So we can say the angular displacement is equal to x over r. So let's call this equation 1. We have seen the different units in which we can express angular displacement. So let's see, is it possible to convert from one unit to another? So let's see how to convert between degree and radians. Between degrees and radians. We have seen that the arc length here of an entire cycle of radius r is equal to the circumference of the cycle. So that we can say that angular displacement is equal to the circumference of a cycle over the radius. Circumference of the cycle over this radius. So from here, we have this. So based on this, and this is equal to 360 degrees. So we can say that 1 radians is equal to 360 degrees over 2 pi. And if you simplify this, you will have 180 degrees over pi. If you simplify further, you will have this. So please let's take note, we shall be using this as we make progress in this class. So all we are saying that angular displacement has 3 units, the degree, and in 1 degree we have 300, in 1 cycle we have 360 degrees. Another unit is revolution. And For an object completing a cycle that's covered 360 degrees. Then the other unit is radians. And from definition of angular displacement, using this figure here, we say angular displacement, which is theta, arc length over radius. This is the arc length. So if you substitute, we have equation 1. Then, to see how we can convert between degrees and radians, we have that for an object completing a cycle, the circumference of the cycle is 2 pi r, which is the arc length, over the radius. So if we simplify, we will have this. So from this, we can get 1 radius. So this is the relationship that if 2 pi is equal to 360 degrees, if 2 pi radians is equal to 360 degrees, then it means 1 radians. When you divide, simplify, you will have this. So 1 radians is equal to this, 2 radians is equal to this. Is that taking? Okay, let's solve some example for us to understand more. Example 1. Synchronous communication satellites are put into an orbit whose radius is 4.23 times 10 raised to power 7 meter. The orbit is in the plane of the equator, and the 2 adjacent satellites have an angular separation of 2 degrees. Find the arc length that separates the satellites. Solution. The radius this is the radius given, then the angle 2.0 degree. Let me give the sketch of the equation. You have the planet and 2 satellites at angular displacement 2.0 degree from each other. This is the radius. So you have 1 satellite here, and another satellite So this is the pictorial diagram of what we are looking at. We have 2 synchronous communication satellites, which are at angle 2 degrees from each other. And the radius is given. So we are to find the distance of separation, which is the arc length. So the first thing we'll do here is to convert from degrees to radians. We have seen that 2 pi radians is equal to 360 degrees. So how many radians will be equal to 2 degrees? So if we simplify, we will have 2 So this is the equivalent of 2 degrees in radians. So we can have that the arc length, we say our angular displacement is equal to arc length S over R, that equation 1. So from here, arc length will be equal to theta R. So let's substitute. So if we substitute and simplify, this is the arc length. Is it difficult? So from the equation, we have two satellites. At an angle, this is the radius. So we convert from degrees to radians and then use the formula. Substituting, we have the arc length. Okay, let's look at other things. We want to look at tau. When a force is exerted on a rigid object pivoted about an axis, the object tends to rotate about this axis. The tendency of a force to rotate an object about an axis is measured by a quantity called tau. So if you have an object, for instance, ceiling fan, so you apply a force to it, it tends to rotate about the axis. So the tendency of the force to rotate an object about an axis is measured by the quantity called tau. So tau is a measure, tau is the measure of resistance. So tau is defined as the product of force and the perpendicular distance of the line action of the force. So mathematically, tau is equal to force times the distance. We say it's the product of the force and the perpendicular distance from the line action of the force. And if the force acts at an angle to the distance, then we can say that tau can be expressed as the distance times the force sine theta, where theta is the angle. So if you have, for instance, let's say a mechanic wants to lose a bolt, you use your spanner, then apply a force to it. The force that is being applied here, F, and the perpendicular distance from the line action of the force is what we call tau. So when the force is being applied at this end, the perpendicular distance to the line of action of the force, you discover that through this knot will be able to lose or will be able to be tightened depending on what the mechanic wants to do. So we are saying that the tendency of an object to rotate when force is applied is measured by the quantity called tau. And we are saying that what is the product of the force times the perpendicular distance to the line of action of the force. And I say if the force is acted at an angle, then we have this expression. So we can call this equation 2, then this will be equation 3. Tau can also be defined as the rate of change of angular momentum. The rate of change of angular momentum. So equation 4 is another definition for tau. Says the rate of change of angular momentum. We'll soon be looking at what angular momentum is all about. And tau can also be expressed as the moment of inertia times the angular acceleration. Let's call this equation 5. So these are the equations that we use to compute tau. If we know the force, know the perpendicular distance, we can use equation 2. If you know the angle of the line of action of the force to the perpendicular distance and also the force, one can use equation 3 to compute tau. And also, if you know the rate of change of angular momentum, tau can equally be computed. And also, if you know the moment of inertia of a rotating object and the angular acceleration, equation 5 can equally be used. So we shall be using all these expressions as we solve some example. Permit me to make this remark. Tau is not the same as force. Forces cause linear acceleration, while taus cause angular acceleration. So angular acceleration, tau causes that, while force causes linear acceleration. And the unit of tau is Newton meter. The unit of tau Newton meter. From here, the unit of force is Newton, unit of perpendicular distance is meter. So this is the unit of tau. Then let's look at the direction. When force is applied to an object at a given direction, a given distance, it can either move in a clockwise direction or in an anti-clockwise direction. So let me bring the diagram here so that we can see it very well. So when the force is applied, the movement can be clockwise or anti-clockwise direction. So tau is possible when the force tends to produce a counterclockwise rotation about an axis. So in this case, counter rotation, it is positive. While clockwise rotation, it is negative. So when this force is applied to this object, like I told us in the case a mechanic that tried to lose a nut, when the force is applied, if it is in a counterclockwise, the tau will be what? Positive. But if it is in a clockwise direction, tau will be negative. So let's understand this as we soon be looking at some example. So let's solve some example for us to better understand this. Let me read out the question. Two disgruntled business people are trying to use a revolving door. The woman on the left exerts a force of 625 Newton perpendicular to the door and 1.2 meter from the hub centers, while the man on the right exerts a force of 8.50 times 10 raised to power 2 Newton perpendicular to the door and 0.8 meter from the hub's center. Find the net tau on the revolving door. Solution. This is what we are saying. you have a revolving door, and a woman here wants to open, apply a force, let's call it F1, at a distance R1. So we have a woman here. Then a man here too wants to open the door, apply a force F2 at a distance R2. So this is a man. So this is the pivot of the door. It's a revolving door. The woman is pushing from here to go in. The man too is pushing from here to go in. So tau exerted by the woman minus R1 F1. And the reason is that it's going clockwise. Remember, I said the direction of tau, if it is clockwise, we put negative. So let's substitute and see. From the equation, the woman exerted force of 625 and the distance 1.20. So if we simplify this, we have minus 7.50 times 10 raised to power 2 Newton. Okay, let's look at the tau exerted by the man. So the tau exerted by the man is R2 F2 because it is counterclockwise. So let's substitute 0.8, 10. So if we simplify, Newton meter. So these are the tau exerted by both the woman and the man. The question says we should find the next tau. The net tau should be equal to the one from the woman and the one from the man. So let's substitute. So if we simplify, so this is the tau. And the negative result here means that the nail tau will produce a clockwise movement. That is the implication of the negative. So this is what we are saying. A woman wants to enter inside, let's say a shopping mall or wherever. She's using this a rotating door. She's pushing from this angle. A man who wants to enter is pushing. And we have said that tau is the tendency force times perpendicular distance. So for the door to rotate, to open for the man and for the woman, force has to be applied. So we look at the case of the woman, substituting the distance, the force applied, we have this. And the negative here is due to the clockwise. As the woman push, it will rotate this way. Are we together? Then tau exerted by the man. This is the formula. And because this is positive because it is counterclockwise. So if we substitute, this is the tau exerted by the man. But the question says we should look at the net tau. The net is what? The tau from the man and that of the woman. So this is the one from the woman. And for the man, this is the tau exerted. So we simplify, this is the answer. And the negative here shows that even though the man tried to open the door, the woman tried to open, the resultant tau, based on this negative, we shows that it will move in the what? Clockwise direction. So this is how to solve calculation of what? Tau. I hope there is no challenge. Okay, let's look at angular momentum. Angular momentum is defined as the product of moment of inertia and the angular velocity. So angular momentum is equal to moment of inertia times angular velocity. So L here is the angular momentum, I is the moment of inertia, and omega is angular velocity. So we shall be using this equation as we make progress. The next thing we want to look at is principle of conservation of angular momentum. Principle of conservation of angular momentum. The principle of conservation of angular momentum states that the total angular momentum of a system remains constant or conserved if the net average external tau acting on the system is 0. So this is the principle of conservation of angular momentum. I mentioned moment of inertia here. Let's look at what moment of inertia is all about. Moment of inertia. The moment of inertia of a body is a measure of the rotational inertia of the body. We can say that it is the reluctance of a rigid body to change its state of rest or rotational motion when no tau is applied. Moment of inertia can equally be defined as a measure of the resistance of an object to changes in its rotational motion. For an object that is rotating, for you to stop it, that tendency to continue to rotate, that resistance from stopping it, or object that one wants to put in rotation. So we say moment of inertia is the measure of the resistance of an object to changes in its rotational motion. So we can say that an object with small moment of inertia has little rotational inertia and tends to rotate easily on the application of a small force, while an object with large moment of inertia is difficult to set into rotation. So moment of inertia, it depends on the mass of the object and the direction of the mass in the object about the axis of rotation. So mathematically, moment of inertia is equal to mass of an object times the radius of gyration. So this is the expression that we use to calculate moment of inertia. I is the moment of inertia. which is the measure of the resistance of an object to changes in its rotational motion. M, the mass of the object. K, or R, as the case may be, is radius of gyration. Radius of gyration. And the radius of gyration is the perpendicular distance from the axis of rotation to the point where the object mass appears concentrated. And it is measured in meter and varies for different shapes. So different shapes has different formulas and value for radius of gyration. We shall be looking at it as we make progress. So let's look at center of gravity. Center of gravity. The center of gravity of a rigid body is the point at which its weight can be considered to act when the tau due to the weight is being calculated. Or we can say the point of an object where the mass is concentrated. You have an object of this nature. If you want to lift it, if you hold it here, you may not be carried easily. But if you hold the center here, where the weight is concentrated, you will be able to lift the object. So we are saying that what? Center of gravity of a rigid body is the point at which its weight can be considered to act when the tau due to the weight is being calculated. Okay, let's make progress. Let's look at equation of rotational kinematic. And we shall be comparing it with linear equation. So let's look at it. Rotational motion at constant angular acceleration. Linear motion at constant linear acceleration. So we are trying to look at equations of motion, try to look at rotational motion and comparing it with the equivalent under linear motion. So in the case of rotational motion, you have angular velocity final is equal to initial angular velocity plus angular acceleration times time. In the case of linear motion, is given by this expression. Final velocity, initial velocity, plus linear acceleration times time. Okay, let's look at second equation of motion. So this is the second equation of motion in the case of rotational motion. Let's look at the equivalent in the case of linear motion. The third equations of motion, let's look at it in terms of rotational motion. In terms of linear motion, it is expressed as this. Are you following? Okay, let's look at the last equation of motion. In the case of rotational motion, Okay, what is the equivalent in case of linear motion? This is the equivalent. Is that taken? So we shall be using this expression to solve some problems. Let's look at example. Example. A wheel rotates with a constant angular acceleration of 3.5 meters per second square. If the angular speed of the wheel is 2.0 radians per second at t equal to 0, through what angular displacement does the wheel rotate in 2.0 seconds? Through how many revolutions has the wheel turned during this time interval? What is the angular speed of the wheel at time equal to 2 seconds? Solution. The first question is on angular displacement. And angular displacement is given by this. From this equation of rotational object, angular displacement, based on the parameter, we can use this expression. So let's substitute. So if we substitute, from the equation, we know the initial angular velocity, the time is given, angular acceleration, and also the time. So if we simplify this, we will have 11 radians. And we can convert this 11 radians to degree by multiplying. If we multiply, we will have our answer in degrees. Remember, I showed us this earlier, that 2 pi radians is equal to 360 degrees. So this time around, we are converting 11 radians to what? Degrees. So if simplify, you have this. Or you can go straight, 360 degree, 2 pi, you have 57.3 degrees. That is how we got this here. So we have gotten the first part. The second part, to get the number of revolution, we use number of revolution, angular displacement is equal to this value in degrees, 630 degrees, 1 revolution over 360 degrees. So this is the revolution. Then the third part says angular frequency. Angular frequency, let's look at the formula based on the parameter. We can use equation 1, that the final angular frequency plus this, if we substitute 2.0 plus 3.5 times 2. So from here, we'll get 9.0 radians per second. So that is the angular speed of the wheel. So based on this, we were to find the angular displacement which we have gotten in radians, and also through how many revolutions has the wheel turned during this time period. We converted and we got this. And the last question say, what is the angular speed of the wheel at time 2 seconds? At 2 seconds, using this expression, this is the angular speed. I hope it's not difficult. So this is how we use rotational equation of rotational kinematic to solve problem. So all we need to do is to remember the equations, and when we have any problem, know the one to bring in based on the given parameters, and also simplify and substitute. Okay, let's make progress. We want to look at rotational kinetic energy of a rigid body.